Hello, everybody. Welcome to a new edition of the ICTS String Talks. This week we have Jack Holden from Southampton, who's going to tell us about partial deconfinement. Jack, the floor is yours.
Well, thank you very much for giving me the opportunity to speak to you at the ICTS today. I'm going to be talking to you about a phase of gauge theories known as partial deconfinement or partial confinement. And I hope to show you that's a very interesting and rich topic of study. So first, I'll give a very brief overview of what partial confinement is and why it's interesting. Then I'll cover some facts which will probably be familiar about regular confinement. Next, I'll introduce what's the state of the art in our knowledge about the partially confined state before the new work that I'll introduce concerning the dynamics and flux tubes in the partially confined phase and global symmetries and order parameters associated with partial confinement. And then finally, I'll speak about how partial confinement relates to questions in holography and QCD. So I'll start with something familiar. This is the first order phase. This is the phase diagram for ice-water transition, and it shows a first order transition in the canonical ensemble where you fix temperature. And I want to draw your attention to this part of the phase diagram. So there are states along this transition temperature which are a mixed state of ice and water, where ice and water coexist at different points in space. So this will be familiar if you've seen ice melting, and there'll be a coexistence of an ice-water state at 0 degrees Celsius. So this is the phase diagram for 4D n equals 4 CPM mils compactified on S3, and it shows something similar, but also quite different. So this again shows the first order phase transition, but instead of ice and water, we have the confined and deconfined phases. So it's possible in n equals 4 CPM mils for the confined and deconfined states to separate in space, just as in the case of ice and water. But that's not what's happening here. Instead, along this saddle, we have a phase in which the confined and deconfined states are mixed in color space instead of the space of space-time. And so this is a cartoon of what I mean, and I'll explain this in much more detail later and explain how this is gauge invariant. But at the moment, I'm just going to give an outline. So if we take some adjoint matter, like a gluon field, a subsector is in the deconfined phase and a subsector is in the confined phase. So a big difference between color space and space-time is that space-time interactions must be local, whereas in color space, the interactions are not in general local. And so in the case of ice and water, non-trivial dynamics can only happen at the intersections in space. And that's why we get a much simpler phase diagram when we look at the case where the mixed state is mixed in spatial separation. Whereas here we get this more complicated saddle with negative heat capacity. And as to whether the diagram, as to whether the splitting occurs in color space or in space-time is a highly dynamical question. And so it depends on the details of the theory. But we also have phase diagrams which look like this in matrix models where there's no color space. So the splitting has to be occurring, where there's no physical space. So the splitting has to be occurring in the color degrees of freedom. So I'll explain now why partial confinement is an interesting study. So we claim that you need to understand the partial phase in order to understand the quark gluon plasma. and in particular the so-called crossover region. So I think I have something very interesting to say about the crossover region at the end of my talk. But the quark gluon plasma is important because it dominated, it's the phase that dominated the universe a few microseconds after the Big Bang. And what occurred here will have consequences for the rest of cosmological history. Something like the quark gluon plasma appears in colliders such as RIC at the Brookhaven National Laboratory or ALICE at the LHC. Partial confinement also governs dynamics and thermodynamics of Kähler space in general. So gauge theories that so it would be a feature of gauge theories in general. And so if gauge theories emerge in condensed matter systems or beyond the standard model, then it's likely that the partially confined phase will appear in some form. And then finally, there's gauge gravity duality. We think that the partial phase has to have a dual in the bulk theory, and we can perform field theory calculations to learn about the thermodynamics of black holes.
Sorry, the HRG on the picture is a Renault group, or what is HRG?
This is an approximation that's used, hadron resonance gas approximation. So this is a region where there's an independent calculation to confirm that the lines of the lattice calculations in this region.
Thank you.
Okay. So I'm going to cover some facts which I expect will be familiar about confinement that I'll use when investigating partial confinement. So I can go into much more detail about any of these, but I intend to go through them quickly because I'm sure they'll be familiar. So the first fact is that a temperature can be introduced into a theory by rotating to imaginary time and compactifying on a circle of circumference 1 over temperature. So in this case, bosons will take periodic boundary conditions while fermions take anti-periodic boundary conditions. Next is the defining feature of confinement, which is that flux tubes form to bind matter into Kähler singlets. And in particular, in any theory in which center symmetry is not explicitly broken, we can characterize confinement by a linear potential forming between a quark-antiquark pair. So this is what I mean. The gluonic flux is concentrated into a tube in a confining theory, and by Gauss's law, it can't dissipate. So the potential has to go linearly with the separation. Whereas for a deconfining phase, the flux isn't concentrated, and so the potential is sublinear. For example, in the Coulomb phase. So that was the flux potential, but we need a precise gauge invariant way to talk about the potential between quarks, and for that we have the Wilson loop. So the Wilson loop is the trace of the holonomy and is gauge invariant, and if it's taken in the fundamental representation, it can be thought of as an insertion of non-dynamical quarks, and then what's measured is the potential between the quarks. So you can see this in detail using the operator formalism, but I'll just show it here heuristically now. If we take a quark-antiquark pair along this curve C and propagate it under Euclidean time for very long distances, it measures the potential between the quarks in an exponent integrated over the Euclidean time. And so if the potential between the quarks is linear, as we expect in the confining theory, this gives us the familiar area law of the Wilson loop, which is known as the signature of confinement. So at finite temperature, we make use of this property in a slightly different way. So because of the compact temperature direction, we can't take a very large curve around the time direction. So instead we take a Wilson loop wrap like this. So these loops go around the whole temperature direction. And so they can be thought of as an insertion of quarks held at a constant point in space and separated by a distance L. So if we think of the operators, the operator P dagger creating a quark and P an antiquark, we can then measure the correlator of these two loops, which measures the potential between the quark-antiquark pair. You can show in detail that this this line acts as the identity. So that's shown in detail in our paper, but intuitively you can think of this as creating an open string and instantly destroying it before it gets the chance to propagate and interact. So this is acts as the correlator between these two loops, and so I use the letter P because these loops, which are Wilson loops taken over the temperature direction, are known as Polyakov loops. And Polyakov loops are very interesting for their own sake, which brings me to the fourth idea in the fully confined phase that I'll be making use of in this talk. So Polyakov loops are very significant, and I'll talk about them in quite a bit of detail now. A single Polyakov loop is an order parameter for confinement, and its associated symmetry is center symmetry, and it can be thought of as measuring the free energy for a single quark state, and I'll discuss these points in detail now. So this is a Polyakov loop, Wilson loop taken around the temperature direction, but this is a very important point. It turns out to be very useful to consider the holonomy over the temperature direction without taking the trace over the colors. And this is what this object P in blackboard bold denotes. It's the Wilson loop without taking the trace. So in the fundamental representation, it's a matrix in color space. And it's best represented by its eigenvalues, which are all phases. And so these eigenvalues can be plotted on a circle or the complex plane if you prefer, with the arguments taking values between 0 and 2 pi. So the reason why this is so useful is this. So the Wilson loop was useful because it was gauge invariant, but this pre-traced Polyakov loop is gauge invariant up to permutations of these eigenvalues. So it just permuting the eigenvalues just swaps entries in the matrix, or what these labels refer to in this circle. So the eigenvalues of P and a representation of the eigenvalues like the circle are effectively a gauge invariant property of the theory and have physical meaning. So the Polyakov loop by itself is so important for this reason. So if you remember this correlator that I told you about before, in a confining theory, we expect the potential to go to infinity as we separate the two Polyakov loops infinitely. But by the cluster decomposition principle, this correlator should factorize. And so we can learn about the insertion of a single quark. So in a confining theory, we know it takes infinite energy for the quark state to appear, and hence the expectation value for the Polyakov loop must be 0. Whereas in a deconfining theory, the potential between infinitely separated quarks is finite, and single quarks can appear. So the expectation value of the Polyakov loop P is finite. And so here, this is why the Polyakov loop is an order parameter for confinement. It's ever in the confining phase and finite in the deconfining phase. An order parameter is usually associated with a symmetry. And so investigate what the associated symmetry is for the Polyakov loop. Now, so it turns out that the Polyakov loop holonomy takes a distribution like this in the confining theory, which clearly looks very symmetric. And it has symmetry under the center of the gauge group, which acts to shift the eigenvalues. So the Polyakov loop, Polyakov holonomy is therefore charged under the center of the gauge group, which is isomorphic to Zn. And we say it has center symmetry in the confined phase. In the deconfined phase, there's no such symmetry of the holonomy, and the Polyakov loop transforms non-trivially under the center of the gauge group, as can be seen if you try to shift these eigenvalues. So our conclusion is that the Zn center symmetry is a signature of confinement, and the Polyakov loop measures it. So these are all the everything that will be useful to us when we go on to speak about partial confinement. Which I will now discuss what was known about partial confinement, which was the state of the art until quite recently. But in what I'm about to say, I will be assuming that we're in a large n, the large n limit of the gauge theory in some group of center symmetry like SUN or UN, and also that there'll be no quarks or fundamental matter. So this can't apply to something like QCD. So a good example to have in mind would be something like large N, UN, or SUM pure Young-Mills. So this is the cartoon again. So as I explained before, in the partially confined phase, adjoint matter will split like this, where we have an SUM deconfining subgroup and an SUN-M confined subsector. Whereas if we had fundamental matter, it would look like this vector representation where M of the colors are deconfined, or N-M of them are in the confined phase. And this situation was first articulated by Hinada and Maltz and David Berenstein, and there's a recent review on this partial confinement story given last month by Hinada and Watanabe. So now those matrices and cartoons I just showed you don't mean much yet. So let's look at a special case of a matrix in a partially confined phase. And we'll use the Polyakov holonomy, this blackboard P. Also we're in the large n limit, so there'll be a large number n of eigenvalues. So it will be more convenient to discuss the density distribution denoted by rho. So this is the confined phase. As we saw before, there's the eigenvalues are uniformly distributed, and so the density will be uniform. In the deconfined phase, the eigenvalues are non-uniform, and so we say that this is the density distribution. And it's important to point out that the eigenvalue density distribution loses support in some area where there are no eigenvalues, so there's no eigenvalue density. So now for the partial phase, we expect a mix between these two. So some of the eigenvalues are uniformly distributed, and we say that this acts like the confined phase. So the confined subsector corresponds to the uniformly distributed eigenvalues, whereas the deconfined eigenvalues are non-uniform. And so the density distribution will look like this, where it's non-uniform, but also it has support for all eigenvalues. So this means that in the partially confined phase, we can read off the number of deconfined colors by the density of eigenvalues at the lowest density. So in the fully confined phase, the number of deconfined colors m is 0, and so the density is 1 here, and it will be uniform. Whereas in the fully deconfined phase, where m goes to n, then the density at this point goes to 0. So this is a precise way to define the phases at large n. We say the confined phase is uniform, the partially confined phase is non-uniform but ungapped, and the deconfined phase is non-uniform and gapped, because we refer to this this area of no support as a gap. And we'll be particularly interested in the transition between the partially confined and the deconfined phases. So this is known as the Gross-Witten-Wodjier transition, due to analogous work done on the 2D lattice, which showed a similar pattern between the eigenvalue densities and a third order distribution there. And the critical point will be when the distribution has this shape, where the distribution just begins to lose or gain support at these points. So the density can't go lower than 0, which is why going between these two configurations signals an important change in behavior. But remember that this characterization is only precise in the large n limit. So when we go to finite n, we lose the continuity in the distributions, and in fact the density will not be 0 at finite n, even in the fully deconfined phase. So we can't use this characterization at finite n. But here's an animation to make it very clear what's happening. So this is the partially confined phase. This is the Gross-Witten-Wodjier point. So the deconfined phase, and then the Gross-Witten-Wodjier point again, and then we move from the partially confined phase to the confined phase. Okay, so these are the two possible patterns of the gauge theory diagram. So on the y-axis, I have the Polyakov loop, which behaves like the energy, and on the left we have a first order phase transition. So this is the confined phase, where p, the order parameter, is 0, and the deconfined phase, and between them is the partial phase, smoothly collecting them. And so this will show a first order phase transition where the partial phase is never favored. So as you move along the confined phase, at some point the free energy of the deconfined saddle becomes lower than that with the confined saddle, and so the system will jump to the more favored saddle, and we would never see the partial phase in the canonical ensemble as a favored saddle. But another possibility is this diagram where the partial phase is stable in the canonical ensemble, and as to which diagram you get, just it depends very much on the details of the theory. And as was shown by Aharoni and his collaborators, we can move from a situation where the partial phase is unstable to one where it's stable by perturbations. So we claim that we can learn about the stable case from the unstable saddle, since they are parametrically linked. So a natural question might be, why do we have the SUM and SUN minus M subgroups rather than something more arbitrary without symmetry. And the answer is actually because of bosonic interference, like in a Bose-Einstein condensate. And
so is this type for SUN minus M?
sorry, pardon?
So is this a typographical error for S, not SN minus M, but SUN minus M?
Oh, sorry, yes. That should be an SU. Ooh. Yeah, sorry about that typo.
Okay.
Yes, sorry about that. Yes, so the reason for the SUN minus M subgroup is the same reason that a condensate forms in Bose-Einstein condensate. The confined phase is analogous to the Bose-Einstein ground state, and it's enhanced because of the SUN minus M gauge symmetry. So in a Bose-Einstein condensate, bosonic particles are identical, and they have redundancy or gauge symmetry under permutation of the particles. So if a set of particles are in different energy levels, then labeling them is highly redundant, and we can project out to get the gauge invariant state. So when we project out to get the gauge invariant state, we must correct for this for the overcounting, and whereas if particles are in the same energy level, then there's one label which corresponds to one state, and so for this reason, particle states which have this permutation symmetry are effectively enhanced over situations like this. So this becomes a very strong effect at large N, and where the condensate ground state is favored over is enhanced by this permutation symmetry, and something analogous happens in the partially confined phase, where the confined subsector is enhanced because of this SUN minus M subgroup. So another question is, why is the block in the upper left? And the answer is simply that we gauge fix to make this so. And so all of these are gauge equivalent. And we can also have something with much more mixing, where the deconfined and confined blocks mix. Any gauge transformation is possible, and they will all be gauge equivalent. And so to construct, for example, a gauge invariant eigenstate under the SUN, we take all of these different gauge configurations, which are related by an SUN transformation, and project them onto an SUN invariant state by integrating over them. So these are some questions which haven't so far been answered in this story. So a very natural question is to think about what the dynamics of the theory might be. What do flux tubes look like in the partially confined phase? And what about their potentials between quarks and particles, since everything so far has been kinematic? Next, we know that center symmetry is an order parameter for the fully confined phase, but are there order parameters for the partially confined phase and associated with global symmetries? And then finally, everything I've said has only been precise in the large N limit, and want to find a way to be able to talk about the partially confined phase at finite N. And so I'll answer these questions in the next two sections. So first we have to take analyze the partially confined phase in a particular theory. And so we'll take Pyongyang mills in the large n limit at strong coupling on the lattice. So the reason why we take the large n limit is so that we can perform Iguchi-Kawai reduction, which makes the computation much more feasible. Whereas by taking the strong coupling limit, what I mean is that we drop magnetic terms in the lattice. So this is the familiar action for Pyongyang mills, and so and we place it on the lattice. Okay. And so you might be familiar with Iguchi-Kawai reduction. What this allows us to do is to place the theory on a single lattice site, and we can calculate correlators on a single lattice site, which would give us the same answer that we would get if we had the full lattice. So some people might be who are familiar with their work might wonder about why it applies in our case. And I'll just say briefly that the center symmetry in our system remains unbroken. And so that's why we can use the Iguchi-Kawai reduction in our situation. Okay, so the phase diagram in our model is of this type, where the partial phase is unstable. And in the canonical ensemble, this means that the saddle is unfavored, but we need some way to be able to probe the saddle. So we do this by adding a cross term to our lattice model to restrict to a certain region of the Polyakov loop. So this effectively puts us in the microcanonical ensemble, and we can probe the saddle by varying the value of P fix at fixed temperature. So let's start with what we know, which is the fully confined case, and the Wilson loop or the Polyakov loop correlator should measure the potential between quarks. And because we're at large n, we have an analytic solution for this, and we find this parameter, which is related to this parameter sigma, which is related to the string tension, will be 1.724 in the units of lattice spacing. So using the setup I described before, we constrain P to be 0, so that we're in the confined phase, the fully confined phase, and we can plot the Wilson loop, which is the correlator between the two Polyakov loops, on a logarithmic y-axis. And so this will give us the potential, and indeed we see that we have the linear potential with the correct gradient of 1.724, and so everything agrees. But now we want to do this for the partially confined phase, and we claim that expect the confined and deconfined subsectors will behave differently. So we need a way of being able to talk about these different subsectors, and for that we construct these operators p-con and p-dagger-con. So to form these, we project onto the confined and deconfined subsectors. So we form this object by p-dec by projecting the deconfined by projecting out the confined sector, and so we have zeros for eigenvalues which correspond to confined eigenvalues, and all the entries are correspond to deconfined eigenvalues in this object P-dec. Whereas in P-con, we have the converse, where we project out the deconfined subsector, and we're left with an object expressed only in these confined eigenvalues. So then we can calculate these two correlators between the confined Polyakov loops and the deconfined Polyakov loops. And our conjecture is that the correlator between two of the Polyakov loops projected onto the confined subsector will behave as if flux tubes form with a linear potential, whereas the deconfined correlator will correspond to something like the deconfined phase, where the potentials sublinear between the quark and antiquark pair, or between the Polyakov loops. And we can refine our conjecture further by claiming that the string tension doesn't depend on the size of the confined sector, and that the only difference between the fully confined and the partially confined subsectors will be that the number of colors. And so if we account for these by simply accounting for the different number of colors in the Wilson loop, then we should expect to see the same gradient of the potential that we calculated for the fully confined phase. So now we probe the saddle by choosing some value of P. And so in order to be able to define P-con and P-dec and make measurements, we have to know how to fix the gauge and identify the confined to deconfined eigenvalues. And so to do this, we run a simulation first, just to get the number of deconfined colors M for the value of P fix we've chosen. And then we run a second simulation where, now that we know M, we can sort the eigenvalues into the uniform and non-uniformly distributed eigenvalues, or the eigenvalues corresponding to the confined and deconfined phases. And then we can construct these objects P-con and P-dec and make measurements. So this is what we'll do now. So first we're setting P to be, constraining P to be 0.2, which puts us a point on the saddle, which happens to correspond to the about half the colors being deconfined. And so again, we'll plot on a logarithmic axis, and so the line we'll see will represent the potential between quarks separated by L. And indeed, we find a linear separation for the quarks in the confined subsector. And furthermore, we calculate the gradient is what we expect it to be based on our conjecture and the analytic result known for the fully confined phase. Whereas if we look in the deconfined subsector, we see that there's no such linear potential between the Polyakov loops. We can do this at another point along the saddle. This time we pick P for 0.25. And again, we see this linear potential in the confined subsector with a gradient in agreement with our conjecture. And in the deconfined subsector, we see no such linear separation, no such linear potential again. And a natural question is maybe, what about the mixed correlator? And we have an argument where we state that if we assume that the state destroyed by P-dec overlaps at all with the lightest mode created by P-dec-con, which will happen in general, then again we should expect the area law or to be the potential to be linear again in the separation. And again, this is what we find. So our conclusion is that the confined subsector in the partially confined phase behaves as if flux tubes are forming between matter in that subsector, whereas in the deconfined sector it behaves like the deconfining phase. So now I'm going to talk about global symmetries and order parameters associated with the partially confined phase. So confinement and deconfinement have center symmetry to distinguish them as an order parameter. But does anything analogous happen for the partial phase? So we know that center symmetry breaks here. So that means that our focus will be on around the what in the larger limits known as the gross written Wodgier point. The transition between the partial and deconfined phase. And we want to know whether we can find any other symmetry breaking that occurs just at this point. So we look again at the theory that we just I showed you before, that we calculated on the lattice, and we introduce probe Dirac fermions, which allows us to discuss chiral symmetry. And so we see that in this theory, in the confined phase, the center symmetry is unbroken, and whereas the chiral symmetry is broken. In the deconfined phase, we have broken center symmetry, but chiral symmetry is restored. And so it's natural conjecture that in the partial phase, both of these symmetries might be broken. And there's also the anomaly argument and anomaly matching, which would strengthen this conjecture. So this is how we'll check. In this case, we want to see whether chiral symmetry breaking or restoration will coincide with the gross written Wodgier transition, which is known to occur at this value of p of 0.35. So we probe along this saddle at different values of p to check for where chiral symmetry is restored. And then we find indeed that it's restored at this value p 0.35, which coincides with the gross written Wodgier transition. So that would seem to suggest that the partial phase can indeed be characterized by center and chiral symmetry both being broken. And so we do this in practice by plotting the eigenvalue distribution at different values of p, and seeing the distribution which characterizes the gross written Wodgier transition. And then we check for an order parameter for chiral symmetry breaking, which is known from random matrix theory, that this corresponds to eigenvalues of the Dirac operator at the density of these at valued at 0. And so this is the summary for this large N UN angles that we've looked at. We have the global symmetry breaking and the linear potential in the confined subsector. So now I'm going to introduce another system, and this will help us to learn about the finite N case. So this is SUN n equals 1 deformed super Young Mills on R3 equals S1, and taking the theta vacuum to be equal to pi. So this is the action for this theory. We have the gauge term, the topological theta term, the fermion kinetic term, and the mass term. So by deformed super Young Mills, what I mean is that we take n equals 1 GPM mils, which has one adjoint viral fermion, and then we add a small mass to the fermion mass, small mass to the fermion, and so this will break supersymmetry. And so this is the conjectured phase diagram for this theory, and will be in this region, which is under control and so well understood. And the deconfinement transition occurs at small radius, which means that we can use weak coupling analysis in this region. But we also expect that as we take the fermion mass to the infinite, then the fermion will decouple and will recover thermal Yang-Mills. And it's thought that this transition between the confined and deconfined theories continues between this area that we're looking at and the pure Yang-Mills case. So let's see. So in this case, we're at theta equals to pi. So this allows us the action to have CP symmetry. And in this case, we find that the confined phase has center symmetry, while the CP CP symmetry is broken. In the deconfined phase, center symmetry is broken, while it has unbroken CP symmetry. And there's also this anomaly from this famous paper, which says that at least the center or the CP symmetry must be broken. So it's natural to conjecture that the partial phase will be characterized by both of these symmetries being broken. So to test this will be our approach. First, we find the partial saddle, and then next we check for transitions occurring at the point between the deconfined and the partial saddles. So we find the partial saddle by so the action that I showed you reduces to this simple matrix model in the limit of small radius, and so we can solve for the saddle point, and this allows us to obtain this partial phase, which connects between the deconfined saddle and the confined saddle. So this is what we would expect for the partially confined phase. And we can do this also at finite n. So this is the case for n equals 30, where we get the familiar swallowtail pattern, where the free energy of the partial phase connects smoothly the deconfined and the confined phases. And so if we look very close in this region, we can see the transition temperature between the partial and the deconfined phases is about 32.2. So next we check for the CP symmetry breaking and see if it corresponds to the same point as the partial phase, partial saddle emerging. And so this is the order parameter of CP breaking, and we can see it for n equals 30. We again see that it occurs right at this point of 32.2. And the same is true for all the other values of n that we looked at. So this leads us to conclude that the partial phase can be characterized in this theory by both center and CP being broken. And we check this not just at large n, but at all these different values of finite n. And so this leads us to propose that global symmetries can characterize partial confinement at finite n. And so we can start talking about the partially confined phase at finite n, and we're no longer constrained to large n. And so we can apply this immediately to an interesting result, which was found by Chen and his collaborators in the case of SU2, which is as far away from large N as you can get. Chen and his collaborators found this phase diagram for SU2, where they had the confined phase and the deconfined phase, but these were separated by some mysterious phase in between. The confined phase had CP symmetry broken, and the deconfined center symmetry broken, but this intermediate phase had both broken. And so our explanation for this mysterious phase would be that it's the partial phase or related to the partial phase. And that the reason why this SU2 case was different from the other SUN cases is simply because in the SU2 case, we have this situation where the stable is stable, whereas in the other cases, the partial saddle was unstable. So finally, I'll make some comments about how partial confinement relates to holography and QCD. So we think that there's an argument. So this QCD crossover region is known. You can see from this diagram that the crossover is not a first order transition or a second order transition. But we think that this argument about partial confinement might suggest that it's a third order transition or higher. So the argument can be made this way. So in large NQCD, we know that the phase diagram looks like this, where the partial phase is stable. And so we know that the greater within Roger transition must occur because we're at large N. So it occurs between the partial and the deconfined saddle. And it's natural that chiral symmetry breaking also occurs here. When we go to finite N, we'll lose the greater within Roger transition, but it's natural to expect that chiral symmetry breaking remains. And so perhaps this point here, which is the crossover region, corresponds to chiral symmetry breaking and then a true transition. So by chiral symmetry breaking in QCD, what I mean is that we start off in a limit where the quark mass or the number of quarks is 0, and find chiral symmetry breaking in that case, and then we add perturbations to get to the QCD case, and see that the crossover region is the messy remnants of the true chiral symmetry breaking, which occurs in that original limit. But it's known that pure Yang-Mills is a first order transition. So how could we get this kind of situation for QCD? And again, we use the results of Aharoni and his collaborators that by adding quark mass or number of quarks, we can go from a situation with an unstable saddle to one with a stable saddle. So the quark, so these are some open questions which remain unanswered, but which would be interesting to answer. It's whether in QCD in the quark gluon plasma, is the partial phase stable? Is the crossover a true transition? And does chiral symmetry breaking coincide with the greater than Roger point? And there are also these dynamic questions about what the bound state and dynamics look like in QCD, and whether there's what the collider signature for the partial phase might be. And so now I'll discuss how the partial phase relates to questions in holography. this is the phase diagram for a black hole in ages 5 plus S5. And it's known that the confined region corresponds to this string gas phase, whereas the deconfined region corresponds to the large black hole. But there isn't an explanation for the small black hole. But if we compare to this phase diagram again, this would suggest that perhaps the small black hole is the partially confined phase. And so to answer this, we'd want to try and find where the gross width and Wodge transition occurs in the dual of the black hole phase transition. So if it's right that this is indeed the partially confined phase, then the gross width and Wodge transition will occur at this point. But there are other arguments given by in these papers suggest that the transition actually occurs down here near the Pociński-Horowitz point. And so open questions related to partially confined phase in holography are: where is the gross width Wodge point? What are the precise details of the dual, the partially confined theory? And does the dual of the partially confined phase coincide with any symmetry breaking, which can be seen from holographic calculations? So this is a summary of everything that I've spoken about. We have the linearly confined in potential in the confined subsector, the global symmetries and order parameters, the question about holography and whether partial confinement is the dual of the small black hole, the relation to the quark gluon plasma, especially the crossover region, and an explanation for this mysterious SU2 phase that was found by Chen and his collaborators. And these are the open questions that I spoke about. So that's all I had to say. So thank you very much for listening.
Thank you very much, Jack. Are there any questions for Jack?
I have a question.
Please.
So, is there any scenario where the quark gluon plasma, when it condenses, and the state exists from the plasma phase, blue balls could survive and act as dark matter? Because usually, it's very hard to imagine that all the gluons would simply go inside the hadrons, right? So some of them will survive. So can they form dark matter?
I don't know. I'm not quite sure what situation you're talking about. But you mean in
universe, the quark gluon plasma phase? When you have the QGP phase in the early universe.
Okay, yeah.
So when it exits that phase, can there be glue balls surviving?
I don't know. I haven't thought much about the connection to cosmology.
Okay.
Loga has a question. Loga.
Yeah. Hello. Am I audible?
Hello.
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 Yeah, you are audible.
Yeah. Sorry. So I was just trying to understand this statement that there's some relation between small black holes and partial confinement. And you had also said something about these Polyakov loops where you just block some of them out and so on. What is the relation between this and small black holes? I do not understand this statement. Is the statement that you can compute some eigenvalues and the eigenvalue distributions are different in the small black hole, or what is the
Yes.
Yeah.
So
Could you clarify that comment? If you can.
yes, so we expect that if you looked at the dual theory and like the dual phase theory corresponding to the small black hole and looked at Polyakov loops, then you'd get the eigenvalue distribution which corresponded to the partially confined phase, which means that you'd get the non-uniform but ungapped density distribution. So is that what you were asking?
So the statement is that you can do the different eigenvalue distribution.
Yeah.
Because it's an. So what is the computation here on the holographic side, on the gravitational side?
So it means that well, on the gravitational side, sorry, so I thought when we say it's the partially confined phase, what we mean is you go to the field theory dual and then see that the field theory behaves like the partially confined phase. And so the properties which are relevant for the small black hole are things like that it has a negative heat capacity, and we would expect that you'd be able to see you'd be able to do, in principle, a calculation in the bulk if you took multiply round Wilson loops or multiply round branes, which will correspond to multiply round Polyakov loops in the field theory, and then you should be able to recover the eigenvalue distribution in the bulk using that. But that's not a particularly practical calculation because we'd have to go into a number of brane windings in the bulk, which are on the order of large n, so you'd get back reaction. But that is a calculation that you can do in principle in the bulk to see whether this is the partially confined phase. So I'm not sure if that's what you were asking.
Okay, I'm just wondering, how do you see the small black holes in this canonical ensemble? But okay, but maybe it's not clear to me. But okay.
You mean just from the gravitational side? Well, you can you can solve for saddles of the free energy in gravity, and you will see these small black holes appearing. But yeah, it's just that this is always an unfavored saddle, so people usually don't focus on them.
Do we have more questions? I see no other hand raised. Thank you very much, Jack, for your nice talk. And we will meet again next week for the next seminar. Thank you, everybody, for tuning in.